All right, so now we'll talk about splines or piecewise polynomial interpolants. Okay, so let me sort of just make some remarks about the limitations of polynomial interpolation. So the first of which is that interpolation on equally spaced points can be bad, in the sense that in some cases the maximum error between f of x and the corresponding polynomial interpolant of degree n goes to infinity as n goes to infinity. All right, and the second of which is that the approximation is global, and so what happens then is that bad behavior at one point affects everything. So, if even one data point is bad, for example, it's like that could contaminate the solution everywhere. Okay, so there are a bunch of options to deal with this. So the first one is to use unequally spaced points. So for example, you could find x0, x1, all the way up to xn to minimize the error, right, which is fx minus Pn of x, right, which is this n plus first derivative at some unknown point divided by n plus 1 factorial times x minus x0 all the way up to x minus xn, right? So maybe you could imagine trying to measure how this degree n plus 1 polynomial term behaves. It's like over some interval. It's like and try to choose x0 to xn to minimize that error, right? So this can improve polynomial interpolation. Okay, except that there are some issues, right? A, you may not have a choice as to where the data is given to you. Maybe the data is going to be equally spaced because there's some measurement process which involves equal time measurements. And the other issue is that the approximation is still global. Okay, so that's something you have to contend with. All right, so instead we're going to choose the second option, which is what is called piecewise polynomial interpolation. Otherwise referred to as splines. Okay. All right. So I'm going to try to illustrate this idea with the simplest possible piecewise polynomial interpolant, which is piecewise linear interpolation. Okay, so let's see what happens with piecewise linear interpolation. And the idea is really quite simple, right? Say you have data like so, right? You can just essentially just join the dots, right? So along each of these intervals, each of these subintervals, the function's a linear function, all right, and then you just connect the dots. Okay, so that's sort of intuitively what piecewise linear interpolation is doing. So let's say we have f, and it is defined on an interval between a and b. So you can partition this interval. So a equals to x0 less than x1 all the way up to xn. So x0 is a, xn is b, and then you have this increasing sequence of points. So the idea then is to approximate f by a function, let's call it s of x, with the following properties. Okay, so the first of which is that s is continuous. On the interval from a to b. Okay. So the next thing you want to do is that on each subinterval, xj to xj plus 1, right, s coincides with a linear polynomial. So this is the sense in which it is a piecewise polynomial function. Okay, so s of x equals to, let's call that sj of x, which is aj plus bj x minus xj for x, which is in this interval xj plus 1, where j goes from 0 to n minus 1. Okay, and the third property is that s interpolates f at the breakpoints. Sometimes also referred to as knots or nodes. Okay, and these are the points x0, x1, all the way up to xn. Okay, all right. So again, the idea is quite simple, right? In practice, you just evaluate the function at the knot points, and then you just join those points together. It's like with straight lines, right? So that's the picture we have here, right? This is xi plus 1, and so on. Okay, so if you were to use piecewise linear interpolation, you can ask, the first question to ask is, well, what kind of error do you get? So there's this an error estimate, right? If f is twice differentiable over the interval from a to b, right, then the maximum error pointwise over this interval of the difference between f of x and the spline is less than equal to m over 8 h squared, where m is the maximum of the second derivative over the interval in absolute value, and h is the maximum length of a subinterval. Okay. All right. So let me make a few remarks about this. So the first thing is that piecewise linear interpolation is much better behaved than polynomial interpolation. Okay, and the second of which is that on each subinterval, xj to xj plus 1, right, s of x has all the nice properties of a polynomial. Right? For example, it's easy to integrate, differentiate, and so on. Okay, and the third of which is that the piecewise polynomial, or the piecewise linear interpolant, so piecewise linear interpolant right, is continuous, produces a continuous but non-smooth representation of f. Okay, so that will lead, it's like to other types of piecewise polynomial interpolants where the it's like where on each subinterval the spline restricts to a high degree polynomial, and that additional degree of freedom can then be used to match the derivatives at the knot points as well. Okay, and so we'll talk more about that in a little bit. So let me stop here for now.